Hello guys, my name is Arvind Rai, son of Selvam. Our group is designing a reactor to produce 100 kg per day of polylactic acid (PLA), a biodegradable polymer. Today I'll cover the background synthesis route and key reaction involved. So, what is PLA? PLA is a biodegradable bio-based thermoplastic polyester made from the renewable resource like cornstarch. It's an eco-friendly alternative to petroleum-based plastics. Here are some major uses of PLA like agriculture, medical applications, automotive industry, and also packaging. Okay, next, reactor design, reactor and design types. Reactor and design focus on efficiency and cost reduction. Common reactor include a base reactor for small scale ROP. ROP is ring opening polymerization. I will explain it later. Next is CSTR for steady large scale production. Then twin screw extruder for viscous polymer and also falling film reactor for lactic acid production. Next is typical process condition of producing PLA via ROP. The first is temperature around estimated 140 to 180 degrees Celsius, and pressure is atmospheric or vacuum. The catalyst used is tin octate or nanocomposites. The conversion rates are 70 to 95%. The molecular weight are estimated to 5,000 to 200,000 gram per mole of achievable in industrial reactors. Here are some key factors affecting the performance, which are stirring speed, temperature control, and catalytic activity and purity. Okay, to produce PLA, there are two main synthesis methods. First method is direct polycondensation and second method is ring opening polymerization. We selected the second method, which is ring opening polymerization, because it only contains two steps and its advantage is high molecular weight production and better control for industrial standard. We didn't select the first method because it's low molecular weight and requires coupling agent. As for next is why ring opening optimization is because high molecular weight suitable for mechanical application and Food and Drug Administration of USA approved for biomedical use and catalysis efficiency. The catalyst we are using is 10 octet, gives high purity and light slight reaction compared to polycondensation, which is the first method. Here is the simplified reaction mechanism of ring opening polymerization of lactite. First step is lactite formation. Lactic acid is formed to lactite and produce also water. And next step is polymerization. Lactites produce polylactic acid under the presence of catalyst, which is nanocomposite, under some preset conditions. Okay, next we get into the multiple reaction fast. During processing and use of PLA, there are several reactions occur. Here is list of reactions. These are the main reaction, and the next is side reactions, which are terminal. First one is terminal hydrolysis. As we can see, PN is equals to PLA chain, and PN one minus one is PLA chain that one unit shorter than original. LA is lactic acid, and N is degree of polymerization. And the next reaction is reaction two is backbone hydrolysis. As we can see, is a PK shorter reaction. Here are some of the list of the reaction, which is third one is backbiting, intermolecular transferification, and the fourth one is random chain scission, thermal acidic catalyzed. Here are some simplified reaction of some selected reaction containing main reaction 1, 2, 3, and 4. And here are the rate law of each of the reaction, assuming elementary as reactions.
I'm Farhana and I'm going to continue our presentation with part reaction kinetic. So PLA does not degrade through one single reaction. Based on Gorasi and Pantani, the dominant pathway is hydrolysis, especially above the glass transition temperature where chain mobility increases. You et al. Showed that at high temperatures, backbiting and transesterification also occur, forming cyclic oligomers. Tolini's model adds that random chain scission becomes significant during melt processing. So overall, PLA degradation is all controlled by hydrolysis, transesterification, and thermal scission happening at the same time. So the main reaction represents effective PLA formation or stability, and we use reference U, which is propagation constant of 37,000 liter per mole H at 180 Celsius. The first degradation pathway is terminal hydrolysis, where PLA reacts with water to form a shorter chain and lactic acid. This reaction is faster because terminal groups are more accessible. So the second pathway is backbone hydrolysis, where water attacks the chain internally, producing two shorter fragments. This accelerates molecular weight reduction. The third pathway is backbiting and intramolecular transesterification reaction that forms cyclic oligomers. Both U reference and Tolini reference observe this at high temperatures. The fourth pathway is random chain scission, which is driven by heat or acidity. This reaction breaks the chain at random positions and contributes to rapid molecular weight loss during melt processing. All reactions are treated as elementary. The main reaction depends on monomer concentration while hydrolysis depends on both PLA and water. Backbiting and randomization depend on the PLA concentration. So we use the following constants. K1 is 37,000 for the main reaction, K2 is 0.18 for terminal hydrolysis, K3 is 0.006 for backbone hydrolysis, K4 is 0.015 for backbiting, and lastly K5 is 0.09 for randomization. These values will follow the correct hierarchy reported in the literature, where main reaction much faster than hydrolysis and hydrolysis is faster than transesterification and fission. So the overall rate of PLA is the main reaction minus all degradation pathways. Lactic acid comes from terminal hydrolysis, cyclic oligomers from backbiting, and shorter fragments from backbone hydrolysis and randomization. These expressions are directly used in our CSTR MATLAB model. All rate constants follow the Arrhenius equation. U reference showed that the main reaction increases sharply with temperature, while Gorasi and Pantani reference showed hydrolysis accelerates above Tg. Since our reactor temperature is fixed, we use the constants directly.
So based on the literature review, the chosen reactor for the PLA production will be the continuous third tank reactor CSTR. This reactor is suitable because PLA is produced in a continuous process and the reaction mixture become viscous. And a CSTR will provide good mixing, which help maintain uniform temperature and composition in the reactor. This also makes the temperature and resident time control easier, which is important to prevent polymer degradation. And literature shows that CSTR are able to conduct in stable operation and also high conversion in PLA system. And under typical condition of 140 to 180 degrees Celsius, CSTR is able to achieve 70 to 95% conversion and very low residual lactite around 0.08%, and therefore CSTR will be the most appropriate reactor system for PLA production. So according to Perry et al. 2008, for CSTR, the ratio of length of the reactor over the diameter of the reactor is equals to 2, and we are using the value of 2.5 meter for the diameter of the reactor, so which means that the length of the reactor will be 5 meter. This ratio is commonly used because it gives a good mixing and a practical reactor shape. So basically this will be our CSTR reactor design. This is basically the main reactor vessel, and what we have on top here is for the reactor 1 feed inlet and reactor 2 feed inlet, and it is positioned at the top to allow smooth entry into the well mixed region inside the tank. And then we also have the product outlet here, where it will continuously remove reacted mixture from the reactor. And we also have coolant inlet, which introduce cooling medium into the tank. And then we also have the coolant outlet here, which will remove the coolant after heat exchange, which will ensure effective heat removal and supply. And then next is the inside of the tank, where we can see we will have the stirrer, which is able to ensure that everything inside the tank is mixed well. And also we have the plates or baffle inside the inner wall to ensure that the mixing efficiency increases and also the heat transfer. So this is basically the design of our CSTR.
For the calculation and analysis part, we first assume a reactor volume of 100 liter and a volumetric flow rate of 1000 liter per hour, which gives the resistance time. The reaction rate constant are obtained from the reaction kinetic. Next, we use the F0 function in MATLAB to determine the optimal inertial monomer concentration to achieve our target production. This ensures the reactant operates effectively while maximizing the main product. On the right side is the MATLAB code that displays the calculated data. Then, on the left side, we have the input for plotting graph, which include production rate versus inertial concentration, selectivity versus inertial concentration, and yield versus inertial concentration. This graph allows to see how different feed concentration affect the reaction outcome and how optimizing the process. Finally, the helper function on the right is used to calculate the conversion, selectivity, and yield for both main reaction and side reaction. These are the outputs. To achieve the target production of 100 kg per day of PLA, the required feed concentration is 0.03 mol per liter. The conversion is 99.6%, which indicates that the reactant is efficient. The selectivity value shows the preference of PLA formation over the side product. With higher number meaning the main product is formed much more than the side product. For the yield, the main reaction contribute 96.7%, while the side reaction only contain a very small percentage. The first graph shows production rate versus initial concentration, which has a linear relationship. At an initial concentration of 0.03 mol per liter, the production rate achieved 100 kg per day of PLA. Next, the second graph shows selectivity versus initial concentration, where higher concentration generally improve the selectivity of the main product over side product. The third graph shows the yield of the main reaction versus initial concentration, which rise rapidly at low concentration and then almost constant at higher concentration, indicating that most of the monomer is efficiently converted into the desired product.
So to conclude, our project shows that PLA can be efficiently produced through ring opening polymerization supported by a well-designed CSTR system. By combining literature insights, a clear reaction pathway, and a multi-reaction kinetic model, we are able to achieve high conversion, strong selectivity, and stable production in our simulation. And overall, the study provides a solid foundation for understanding PLA behavior and designing an effective reactor system.